Dear colleagues, let us introduce to your consideration our recent work, Methodology for an Intelligent System Constructing for Modeling the Conduction of an Electrical Impulse in Nerve Axons. This article presents a methodology for building an intelligent system for approximate solution of the Hodgkin-Huxley equation, which models the conduction of an electrical impulse in nerve axons. Given the complexity of this non-linear differential equation and non-uniqueness of its solution, we use advanced computational methods including physical information neural network and deep learning methods. These methods allow us to transform infinite-dimensional stochastic optimization problems into finite-dimensional ones, providing efficient and accurate numerical simulation. Our approach combines machine learning with classical biologic modeling to overcome the limitation of traditional numerical methods. We develop an algorithm that approximates solutions for electrical impulse conduction models by capturing both quantitative and qualitative characteristics of nerve impulse dynamics. Numerical results confirm the effectiveness of our methodology, demonstrating accurate approximation and stability of traveling wave solution for various parameter settings. This research provides a deeper understanding of neural behavior and offers potential applications in the development of new therapeutic strategies. Consider the problem which you can see on the slide. According to the article Evolution, Inclusion and Variation in Equalities, we can say that there is a weak solution. The main goal of this research is to develop an algorithm for approximation of solutions for classes of an electrical impulse conduction in nerve axons with multi-valued interaction functions, allowing for non-unique solutions of the Cauchy problem via physics-informed neural networks. We are going to perform it in three steps approach. First, we need to replace f in the equation with a Lipschitz approximation. Then reformulate the problem as a stochastic optimization problem. Finally, we are going to use neural networks to solve the regularized problem via deep Galerkin method. Here we go to the first step. We approximate the function s by the following Lipschitz functions. For a fixed k, consider the problem with initial conditions. Let's take L, which satisfy the following conditions. For the second step, we reduce the regularized problem to the infinite-dimensional stochastic optimization problem. However, due to its infinite dimensionality, the optimization problem is not yet suitable for numerical computation. Because of that, we transform this infinite-dimensional stochastic optimization problem into a finite-dimensional one by incorporating artificial neural networks. The affine function is defined as following. Finally, we involve approximating the minimizer using stochastic gradient descent optimization methods. Let L defined as following. Ultimately, for sufficiently large k, h, and n, the realization is chosen as an approximation. For the computational methods, we use physics-informed neural networks to incorporate physics laws into neural networks for more accurate modeling. Also, we use the deep learning Galerkin method to convert infinite-dimensional problems into finite-dimensional ones. Both methods improve computational efficiency and solution accuracy. For the numerical implementation for approximating a solution, we use 6 different coefficients A and the initial condition which you can see on the slide. This implementation follows the original proposal where 2000 realization of the random variable and fully connected feed-forward ENN with 4 hidden layers, each containing 50 neurons, and deploying the switch activation function is then trained. The training process uses batches of size of 256 sampled from the 2000 preselect realization of random variables. Optimization is carried out using the ADAM SDG method. On this slide, you could see the result of the numerical execution. So to sum up, we have developed and validated intelligent system methodology for approximating solution. The core of our approach integrates advanced computational techniques, notably physical informed neural networks and deep learning learning method, with biological modeling to address the complexities inherent in this system. We confirm the effectiveness of our method by numerical implementation and empirical results. In future, we are going to give a considerable attention to empirically validating the obtained results through the series of experiments. Also, we are going to apply this approach to the system of discontinuous nonlinearities and to other mathematical models like climatology models, heat mass transfer, etc. Thank you for your attention and feel free to address your question if any.